In the same way that adding and subtracting real number fractions is more challenging than multiplying or dividing real number fractions, the same thing is true for adding and subtracting rational expressions. What makes adding and subtracting more difficult is that a lowest common denominator, LCD, is required. Let's discuss the procedure for how to add and subtract rational expressions. The first thing we're going to have to do is find the LCD for the rational expressions. To identify the LCD, we're going to have to do a lot of factoring. First of all, we're going to factor each denominator completely, and then note each unique factor of all of the denominators. The LCD then is the product of each unique factor, and as we'll see in our examples, we always want to include the highest power of each repeated factor. Now, that may not make a lot of sense at this point, but this is really what we do when we find the LCD for real number fractions. So let's just look at a really simple example to begin with. Let's suppose I've got the fraction 1/6 and 1/8, and I want to find the LCD. Now, a really easy way to find an LCD is to take your largest denominator, in this case it would be an 8, and just list the multiples of 8. So 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24, 8 times 4 is 32, and then we identify which one of those multiples is also a multiple of 6. In this case, 24 is the lowest common multiple, so it would be our lowest common denominator. However, if we want to think about it with this type of reasoning, let's look at the factors, the prime factors of each denominator. So 6 could be written as the product of 2 times 3, and 8 could be written as 2 times 4, but 4 is not prime, so let's rewrite 4 as 2 times 2. So we can think of 8 as 2 times 2 times 2. So to form the LCD, it's going to be the product of each unique factor. So I notice I've got 2 unique factors between 6 and 8. There's a 2 and there's a 3. So I know that my LCD is going to have the factor 2 and the factor 3. However, we're also to include the highest power of the repeated factor. The highest power of 2 in my first denominator is 1, but notice it repeats 3 times in our second denominator. So we would need to repeat it 3 times in our LCD. That is, our LCD would be 2 times 2 times 2 times 3, or 8 times 3, which is 24. Now, that is basically the approach that we're going to take whenever we have rational expressions or expressions that contain polynomials. Once we find the LCD, then here we are at number 2. Write each original fraction as an equivalent fraction with the new LCD. Then recall that when we're adding or subtracting fractions, we take the LCD and transfer it to the answer, and we apply the operation only in the numerator. And then finally, like we do with real number fractions, we want to reduce the final fraction by dividing out common factors. So before we get started adding and subtracting, let's just practice finding the LCD on example 4. So we've got 3 fractions to consider: 2 over x, 3 over x squared, and 1 over 2x squared. Remember, our LCD has to have each unique factor. So looking at our first denominator, the only factor there is x, so we know the LCD has to have an x. If we go to our second denominator, it's x squared. And remember, the rule is we always include the highest power of each factor. So we know we're going to need an x squared. In the final fraction, there's a new unique factor that's introduced. That is 2. So we know 2 also has to be a part of our LCD. And I'm going to go ahead and write it on the left side because we normally put those real number coefficients on the left side. So our lowest common denominator here would be 2x squared. On the next example, we've got 2 fractions or 2 rational expressions, 3 over x plus 1 and 5 over x minus 1. Now make sure that you understand that this whole denominator is one factor. It's got 2 separate terms, but I can't use the terms to form the LCD. So I've got the factor x x plus 1 in the first fraction and x minus 1 in the second fraction. So really, we've got two unique factors. Our LCD must contain each one of those unique factors. Think of your LCD like a representative. It has to reflect each of those denominators in order to be the common denominator. On our last example, again, we've got two fractions or two rational expressions. To form the LCD, we need to be able to identify the factors. So the first thing we want to do on this one is factor both of those denominators completely. So let's break our trinomial here into two binomial factors. Because our leading coefficient is 1, we've only got two possibilities for the first two spots in our binomial factors. The only way to get an x is x. The only way to get an x squared is x times x. Also notice this sign is positive, so we know the signs in our binomial factors are going to be the same. This one tells me they're both positive, so we're going to have a plus and a plus. Now we're looking for two factors of 6 with a sum of 5, or two numbers that multiply to give us 6 and add to give us 5. And our winning pair then would be 2 and 3. So there's the two factors of our first denominator. Let's look at our second one. This one is also going to break down into binomial factors. And because we have an x squared in the first spot, we know we're going to have an x and an x in the first two spots of our binomial factors. Now, because this sign is negative, that tells us we're going to have two different signs in our binomial factors. Remember, we talked about different sign difference. Over here, it was same sign sum. And then this one tells us that our biggest one needs to be negative. So our biggest factor is going to go right here. So we're looking for two factors of 8 with a difference of 2. And the winning pair there would be 4 and 2. The biggest one is 4, so that goes in the negative spot, and the 2 right here. And as always, if you're unsure, you can always check the factorization with FOIL. Now that we can see individual factors, we're going to build our lowest common denominator, our LCD. So looking at the first factor, x plus 2, we know that has to be represented in the LCD. The second factor there is x plus 3. It's distinct and different, so we're going to include that in our LCD. Moving on to our next denominator, the next factor that we see is x plus 2. Well, notice that's already represented in our LCD, so we don't need to add anything there. And then finally, our last unique factor is x minus 4. So that also has to be represented in our LCD. So here's an example of a lowest common denominator that has 3 factors. If I'm adding or subtracting fractions that don't have a common denominator, that's going to be my first step. Find the common denominator. Okay, now that we're warmed up, finding the lowest common denominator, let's practice actually adding and subtracting fractions. Example 5, perform the indicated operation and simplify. Now we're starting out in an easy case. Notice our two fractions on example A have the same denominator. So our common denominator there is x minus 5. So I'm just going to transfer that common denominator to my final answer. Then I'm going to apply the operation just in the numerator. So we're going to have 5 minus 7 in our numerator. 5 minus 7, of course, is negative 2, and our common denominator is x minus 5. So our fraction is reduced, and that could be our final answer. Now, if you gave me that on a test, of course I would give you full credit. But I do want to show you something that you might want to be aware of moving forward. A lot of times we say the simplest expression contains the fewest number of signs. So what I'm going to do is get a little sneaky here, and I'm going to factor a negative 1 GCF out of the denominator. So if I factor out a negative 1, that's going to change the sign of each of those two terms. Then we can see there's a negative in the top and a negative in the bottom, so those two negatives would make a positive. So this leaves behind a positive 2 in the top and negative x plus 5 in the denominator. But I'm going to rearrange that. I'm going to write it 5 minus x instead. So this fraction is actually equivalent to this answer, but this final answer, you could make the argument, is simpler because it has fewer signs. It's a little easier on the eyes. They're both equivalent, but be aware of that trick. The shortcut for doing that trick, again, if you notice the negative right here, you can cancel that just by reversing these two terms to get this final answer. Okay, let's try example B. We have x over x plus y over x minus y. So our first job here is to find the lowest common denominator. So we've got the case of having binomial denominators. Those two factors are distinct, so our LCD must contain each one of those factors. So what I'm going to do is update this old first fraction to having the LCD x plus y times x minus y. And we want to do the same thing for this second one. It's already got the x minus y. I want it to have the new denominator x plus y times x minus y. Okay, we've made changes to each denominator. So if I change the denominator, I have to make the same change in the numerator to maintain the same value for that fraction. So notice from here to here, our old original denominator to our new common denominator, we picked up a factor of x minus y. So we want to pick up that same factor in the numerator. Now our original numerator here is x, but once again, because we multiplied the denominator by x minus y, we want to multiply the numerator by x minus y. Okay, let's update our second fraction. From here to here, we picked up a factor of x plus y. Now our original numerator, of course, was y, but whatever factor we multiply the denominator by, we have to also multiply the numerator by. So that must be multiplied by x plus y. Now, if you look at each of those fractions, it's tempting to want to cancel the common factors, but if we did, we would be going backwards, back to the original problem. So leave it as is. What we need to notice at this point is now they have a common denominator. So I can go ahead and combine the numerators over that one common denominator. So there I'm just transferring the LCD to the answer. Then we'll apply the operation in the numerator. So we're going to have x times x minus y plus y times x plus y. And we need to simplify. To do that, we're going to distribute the x first. That's going to give us x squared minus xy. We've got a plus in between. Here we're going to distribute our y. Y times x gives us yx, but it's customary to put our variables in alphabetical order, so we'll rewrite that as x times y. And y times y is y squared. And I'm going to make no change to the denominator. Notice I'm choosing not to multiply out that denominator. I'm multiplying the numerator, but not the denominator. I want to preserve those factors in the denominator just in case I could cancel later on. Okay, simplifying our numerator, notice these two terms will cancel out, and that's going to leave behind x squared plus y squared over x plus y times x minus y. At this point, we would want to attempt to factor the numerator to see if we could reduce the expression at all. But notice our numerator is the sum of two squares, which does not factor. So this rational expression is completely reduced. Again, leave that denominator factored. It makes it clear that it doesn't need to be reduced any further. Okay, let's try one more example. On part C, we're finding the difference between two fractions with different denominators. So we need to find the common denominator. In order to find the common denominator, we need to factor each one of those denominators. So the first one can be broken down into two binomial factors. Notice we're going to have an x in the first two spots. Because this sign is positive, we know that the signs of our binomial factors must be the same, and this one tells us they're both going to be positive. So we'll have two pluses in our binomial factors. Then we're looking for two factors of 1 with a sum of 2. Well, the only two factors of 1 would be 1 and itself. That's a perfect square trinomial. We could also write that as x plus 1 quantity squared. Taking a look at our second denominator here, we can also break this one down into two binomial factors with an x in the first two spots. Notice our second sign here is negative. That tells us we're going to need two different signs in our binomial factors, one positive and one negative. This tells us that the biggest one is going to be negative. So I know I'm going to put the biggest factor right here. So we are looking for two factors of 2 with a difference of 1. Well, of course, the only two factors of 2 are 1 and 2. The biggest one needs to be negative, so we'll put the 2 here and the 1 here. Now that both denominators are factored, we can properly identify the LCD. The LCD has to represent each unique factor and include the highest power of repeated factors. So by looking at both of these factored denominators, clearly we're going to have an x plus 1, but I'm going to include the highest power, which would be 2, from that first denominator. And also we're going to have to represent the factor x minus 2. Okay, we have a plan. We have a common denominator. So my goal now is to rewrite each of those original fractions as an equivalent fraction with this new LCD. So here we go. I want to rewrite the first fraction with the common denominator x plus 1 squared times x minus 2. Now let's compare the original factored form denominator to our LCD. Notice we picked up a factor of x minus 2. So I'm going to apply that same factor to the numerator. So the original numerator was x, but now we're going to introduce the new factor x minus 2. So we've multiplied the top and the bottom by x minus 2. Okay, updating our second fraction, we need the LCD x plus 1 squared times x minus 2. Now, if we compare the old denominator, of course in factored form, to the LCD, we gained a factor of x plus 1. So we're going to need to gain that same factor in the numerator. That is, I am multiplying the top and the bottom of this fraction by x plus 1. Now that we have a common denominator, we can combine both of those fractions over that singular common denominator. And then we can apply our operation to the numerator. So we're going to have x times x minus 2 minus 2x times x plus 1. Now remember, at this point, we do not want to multiply out the denominator. Leave that in factored form. We're going to do all of the manipulation in the numerator. So let's start by distributing the x. That's going to give us x squared minus 2x. And be careful here, we're not just distributing 2x, we're distributing negative 2x. So that's going to give us negative 2x squared minus 2x. And I'm just going to copy down the common denominator. Simplifying our numerator, we're going to end up with, combining like terms, negative x squared minus 4x over our common denominator, x plus 1 squared times x minus 1. That's pretty good, but notice the numerator can be factored. There's a greatest common factor there. So we always want to present our answer in factored form because that shows you if it's reduced or not. So in the numerator, I'm going to factor out the GCF negative x. That's going to leave behind x plus 4. And we'll put that over our common denominator, x plus 1 squared times x minus 1. Because there's no common factors between the numerator and denominator, we know that it is completely reduced. Now that's definitely going to take some practice. Maybe looking back at real number fractions, you'll think, you know, those really weren't so bad after all. Okay, before we conclude this video, let's look at a quick application of rational expressions. When might you need to manipulate a rational expression? On example 6, we're going to consider a problem involving distance, rate, and time. So recall, distance is equal to rate times time. That's generally how we remember the formula, but we could manipulate that formula to produce something equivalent. For example, if I wanted to isolate t, time, in this equation, I could divide both sides by r. Dividing both sides by r, we would get distance divided by rate equals time. So that's an equivalent formula. It's just been rearranged. So keep that in mind as we work example 6. On a 715-mile trip to college, Paige's average speed was X miles per hour. So we don't know how fast she was going, but we know she went a distance of 715 miles. On her return trip from the holidays, she averaged 10 miles per hour less than her trip to college. So same distance, but she drove a little slower coming home. Slower by 10 miles per hour. The time that it took Paige to drive to college can be represented by 715 divided by x, and the time that it took Paige to drive home by 715 over x minus 10. Okay, you can either take that for granted or you can take a minute to understand it. Notice we're looking at the time that it took Paige to drive to college. According to the second form of our formula up here, time is equal to distance divided by rate. So notice in the top we have the distance that she drove, and in the bottom we have her rate that she drove to college. So distance divided by rate, that's the time that it took her to get to college. On our second fraction here, notice the distance is on top. It's the same, 715, but the rate on the bottom is 10 miles per hour slower than the original rate. But distance divided by rate again gives us time. With that understanding, write a simplified rational expression that describes the total time that it took Paige to drive to college and back home. So we could think about her total time as the sum of the two times. How much time did it take her to go to college? That's 715 over x. Added to how much time did it take her to return? 715 over x minus 10. And we want to simplify this rational expression. Now, in order to do that, we're going to need a common denominator. Clearly, the LCD is going to be the product of those two unique factors, x times x minus 10. And we want to rewrite each fraction as an equivalent fraction with that LCD. Now I'm going to skip one step here, and I'm going to give you permission to do the same if you feel comfortable with this. If you don't feel comfortable with this, add an extra step and write two new equivalent fractions. But we know after we get the common denominator, we end up combining those two fractions over that one LCD. And then we apply the operation in the numerator. So our original first numerator was 715. And notice from the old denominator to the new denominator, we multiplied by x minus 10. So I want to apply that x minus 10 to this numerator as well. Now I'm going to go ahead and write that operation plus in between the two numerators right here in the top. Our second original numerator was 715, and notice from the old denominator to the LCD, we multiplied by x, so we want to do the same thing to this numerator, 715x. Now, as we've been doing, let's go ahead and distribute in the top. So we're going to have 715x minus 7,150 plus 715x, and I don't want to multiply out that denominator. Combining like terms in the top, 715x plus 715x would give us 1,430x minus 7,150, all divided by x times x minus 10. Now that's pretty good, but I'm not sure if it's reduced. The best way to determine if it's completely reduced is to make sure everything's in factored form. So let's work on factoring the numerator. Now I know the numbers are a little bit bigger, but it turns out that 1,430 is the greatest common factor. So if I take that out of the first term, that's going to leave an x behind, and 7,150 divided by 1,430 gives me 5. Now in the factored form, I can tell there's no common factors between the numerator and the denominator, so we have our simplified rational expression. So we got that first task taken care of. Now the next question says, what was Paige's total driving time if she averaged 65 miles per hour on her drive from home to college? So what was Paige's total driving time? Now remember, we just wrote an expression for the total driving time. Now we know that her average speed, which we previously called x miles per hour, is 65 miles per hour. So to figure this out, we're just going to have to plug 65 in for x. So total time at 65 miles per hour. Let's figure that out. So I'm going to replace x with 65 in all places that it appears. And then we can simply type that into the calculator, let the calculator do the arithmetic for us, and we would find out it comes out to exactly 24 hours. So her total time, if she averaged 65 miles per hour, would be 24 hours. So in that problem, we were able to add two fractions together, get a common denominator, and then evaluate it at a specific value for x.